Okay, here's a video that picks up from the one where we talked about, where we defined material dispersion. And just to summarize that, the pulse spreading, delta tau, was equal to minus Lm delta lambda. And therefore delta tau by L, which is the pulse spreading per unit length, which characterizes the fiber. You know, delta tau itself depends on the length of the fiber. We'd like to characterize the fiber, so we write delta tau by L, and it's minus m delta lambda. And this m is non-zero because of the dependence of the silicon oxide, that is the glass's refractive index, on wavelength, and it turns out it's proportional to the second derivative because of some details regarding group velocity of pulses. This is the material dispersion. And what we'd like to do is we'd like to be able to figure out what that is for glass. It turns out that there's a real nice equation that helps us do that, and that's called the Selmaier equation. It's actually an approximation, or the mathematical form of it is actually based upon some actual physical understanding of resonances, for example, within of various types within the glass matrix. But for our purposes, we're just going to write that m is a function of lambda, and we're going to write as an approximate relationship for SiO2 for our glass that m of lambda is m naught over 4 times lambda minus lambda naught to the fourth over lambda cubed. You can see that the second term here is has a wavelengths, has units of meters, as does the first. And in this equation we have two parameters, m naught, which is negative 0.095. Turns out it has units of picoseconds per nanometer squared kilometer. And lambda naught is called the zero dispersion wavelength, and we're going to take that as 1300 nanometers. So this is the zero dispersion wavelength. And it turns out that m naught is the slope of the dispersion curve at the zero dispersion wavelength. So we call this the dispersion slope. Let's see, if we plug in lambda naught, we're going to get lambda naught to the fourth over lambda naught cubed gives us lambda naught, and we plug the same thing in here, we get lambda naught minus lambda naught, and we get 0. So m of lambda naught really is 0, so it is the zero dispersion wavelength. And now we can write, or now we can look at what this plot looks like. This is the dispersion of the fiber. It does depend on wavelength, and there is a zero dispersion wavelength, and the curve looks something like this. I believe it's concave upwards. We can make that plot in Excel if we want. And the slope of that curve at the zero dispersion point is m naught. Okay, and you can do that. You can verify that by differentiating this thing. So that's the Selmaier equation, and we will use that. And as I've mentioned previously, 1300 nanometers is one of those important windows in fiber optic systems. Why? Because the dispersion of the fiber really does go to 0 there. It's a great thing. We'll see it's sort of a double-edged sword. It can be great, and it can also cause some problems. There's the Selmaier equation. I'm also going to tack onto this video a quick derivation of an equation that really is very useful, especially when we talk about DWDM systems and channel spacing in them, but also when we're talking about the spectral width of a source, and we're interested in converting between spectral width in lambda versus spectral width in frequency. So we can characterize a spectral width either as a wavelength range or a frequency range. And of course, C is equal to lambda f, so we can characterize a delta lambda by saying it's something like lambda 2 minus lambda 1, for instance. And we can literally calculate F1 is C lambda 1 and F2 is C lambda 2, and then calculate delta F as F1 or F2 minus F1. If delta lambda is greater than 0, then delta F will be less than 0. We can do that every time if we want. We can just take two wavelengths and plug them in and get our delta F. But usually it's much easier to go ahead and just write, for example, that F is equal to C by lambda. Therefore, doing an implicit differentiation, I get C over lambda squared. Let's see, I have a minus sign, delta lambda. And in other words, what we have is we have that delta F is minus C over, well, what we'll write is that, we're going to write that delta F over F is delta lambda over lambda. It pops right out there. So this is the equation that we'll use quite often. It turns out that the fractional change in frequency and in wavelength and frequency are equal. So delta F over F is the fractional change of frequency. Delta lambda over lambda is the fractional change in wavelength. But as we noted earlier, when delta lambda is positive, delta F is negative, what we'll do to, instead of putting a minus sign on here, I'm just going to go ahead and put absolute values there. And this equation is very useful, as I say, not only in considering the spectral width, perhaps, of a light source, an LED or a laser diode, but also when we talk about the channel spacing in WDM systems. So this is just sort of a fundamental relationship that we'll be using. Thanks.